This video will discuss the Gibbs-Duhem equation in thermodynamics. So to start off, one of the possible definitions we can use for the Gibbs energy is that it's equal to the enthalpy minus the temperature times the entropy. For a mixture of various solutions, the Gibbs energy is also equal to a function of temperature, pressure, and the number of moles of every component in our mixture. Now, we've been looking at partial molar quantities thus far. So if we take this equation and we take the partial derivative with respect to the number of moles of a given component in the mixture, what we get here is the partial derivative of Gibbs energy with respect to number of moles of I at constant temperature, pressure, and number of moles of every substance besides substance I. That equals dH dNi at constant T, P, and N sub J not equal to I, minus T times partial derivative of S with respect to Ni at Tp and constant number of every other kind of mole. So from our video on partial molar quantities, we recognize this to be the chemical potential of substance I. This is the partial molar enthalpy of substance I. And this is the partial molar entropy of substance I. So G equals H minus Ts, and the chemical potential of a substance, which is equal to its partial molar Gibbs energy, is equal to the partial molar enthalpy minus T times the partial molar entropy. Okay, so if we look at the partial molar entropy, that's the derivative of entropy with respect to number of moles of substance I. We also know that the entropy is the negative partial derivative of the Gibbs energy with respect to temperature. So this is d dNi of minus dg dt. Due to the equality of mixed partial derivatives, we can trade the order of operations of these derivatives. So we have minus ddt times dg dNi, which is equal to the negative of the temperature derivative of the chemical potential. So the partial molar entropy of a substance is equal to the negative partial derivative of its chemical potential with respect to temperature. Right, our partial molar volume is equal to the partial derivative of volume with respect to number of moles of that substance, which is equal to d dNi of the volume is the partial derivative of the Gibbs energy with respect to pressure. Trade the derivatives again, we have ddP times dg dNi, or the partial molar volume is the partial derivative of the chemical potential with respect to pressure. Okay, so similarly, just as the Gibbs energy is a function of temperature and pressure, the chemical potential is also a function of temperature and pressure. So we have d mu I, the change in the chemical potential of a substance when temperature and pressure are allowed to vary, is the partial derivative of chemical potential with respect to temperature times dt, plus the partial derivative of chemical potential with respect to pressure times dP. So the change in chemical potential as conditions for the system change, d mu I, equals minus S bar I dt plus V bar I dP, the negative partial molar entropy times dt plus the partial molar volume times dP. Okay, and similarly, I said that G, the Gibbs energy, is a function of temperature, pressure, and the number of moles of N1 and substance 1 and substance 2 if we have a binary or a two-component mixture. So the differential of the Gibbs energy, so dG during some small change in our system, is going to equal negative SDT plus VDP plus mu1 dN1 plus mu2 dN2. So each of these are the partial derivative of the Gibbs energy with respect to each of these individual variables. Okay, so we see that at constant temperature and pressure, so if temperature and pressure aren't varying, dG equals mu1 dN1 plus mu2 dN2. But let's look at another thing now. So we remember that the Gibbs energy is an extensive state function. So if we have a constant ratio of N1 and N2, or what we're going to eventually call the mole fraction of N1 of substance 1 and substance 2. So we're going to increase the amount of each substance that we have linearly. So the Gibbs energy at T(P), where we have lambda N1 moles of 1 and lambda N2 moles of 2, where lambda is just some integer, which we'll say varies between 0 and 1. The Gibbs energy of that system is equal to lambda times the Gibbs energy of T(P), N1, and N2. So if lambda equals 0, the Gibbs energy equals 0. If lambda equals 1, then everything just ends up being 1. If it's 2, it ends up being 2. And we also see that dg here is mu1 dn1 plus mu2 dn2. So what we end up drawing out of this type of equation here, that the fact that enthalpy has to be the Gibbs energy has to be an extensive state function, is that the Gibbs energy of T, P, N1, and N2 is equal to the chemical potential mu1 of T and P times N1 plus mu2 times N2. So the chemical potential of substance 1 times the number of moles of substance 1 plus the chemical potential of substance 2 times the moles of substance 2. All right, so we can take that there. If we take the derivative of this equation here, dg from this equation, it gives us mu1 dn1 plus n1 d mu1. That's the product rule acting on this product, plus the product rule acting on the other product, mu2 n2, mu2 dn2 plus n2 d mu2. All right, so this is a dg for our system. This is also a dg for our system. So we set these two values equal to each other. We get mu1 dn1 plus mu2 dn2 equals mu1 dn1 plus n1 d mu1 plus mu2 dn2 plus n2 d mu2. So the terms where we have dn1 and dn2, those all cancel out because they're equal on opposite sides of the equation. So the result is that, and under conditions of constant temperature and pressure, we have the number of moles of substance 1 times the change in chemical potential of substance 1 plus the moles of substance 2 times the change in chemical potential of substance 2 is equal to 0. So this is called the Gibbs-Duhem equation, and this will relate the chemical potential change of substance 1 to the chemical potential change of substance 2 whenever those are varying during some chemical process.